Welcome to today's lecture on the gas laws. The gas laws are really all about, well, gas, but more specifically about kind of looking at temperature of gas, the pressure of gas, and the volume of gas. And then how all of those relate and what's actually going on. So in today's lecture, we're going to be talking about all of those things and how they're really interacted. We're going to look at three main laws, gas laws. And one is Boyle's law, and the other is Gay-Lussac's law, and the other is Charles' law. Pretty cool dudes. They're scientists from way back when. And they really looked at the interaction of all of these things. And then we're going to put all of those three laws together into the general gas law. We're going to look at examples of each one of those and kind of unpack and study how they all work and what's actually going on. The other thing that's going to be interesting is that we're going to be looking at temperature and what temperature really is and what the difference between temperature and heat is. Yeah, there's actually a difference between temperature and heat. So, and we will touch on a little bit about pressure, and we're also going to be discussing the Kelvin scale of temperature. Okay, so let's just start rolling. So we're going to take a look at maybe volume. We have to define volume. Okay, so we know the symbol for volume is V. And when we're talking about volume, we're talking about like a kind of a three-dimensional enclosed space. I think it's important that we highlight the fact that it's enclosed. So what we're doing is when we're talking about all of these gas laws, there are kind of a couple main principles that we have to look at. One is that it's a completely sealed container that we're discussing. It's not open, it's not in the atmosphere, it's a sealed system that we're looking at. And the other is that it's only one gas. It's not two sealed systems connected together. We're talking about one environment with the same temperature, with the same pressure, and with the same volume. And we may change one or the other, but we're not going to add or remove gas. And we're talking about kind of a sealed system. So the volume of that sealed system is capital V, and we know that there are different ways we can measure volume. It doesn't actually matter in the gas laws what volume you use to measure, as long as you're consistent with those things. So we can measure them in liters, or you're going to cubic feet, or cubic inches, or gallons, and then there's some pretty cool units like, you know, the jigger and the pony and the shot and stuff, and a pint. Now those are volumes specifically for liquids, but you know, I thought I'd put them there because they're pretty cool. And there's a dram, which is a total ripoff because it's 3/4 of a pint of beer. I don't know what's up with that. Okay, let's continue. So those are liquid measures, but we're really talking about volume. So yeah, like I said, we have to define temperature. What is temperature anyway? Like, what's going on? Okay, so the temperature of a substance is related to the mass of the substance, okay, and the amount of thermal energy or heat energy that's in that substance, okay? So I think that makes sense. So there are three attributes. There's temperature, heat, and mass. Okay, so the energy, the temperature, I think really we can say the temperature is related to the amount of heat and the mass itself. So we can say the temperature is kind of somewhat like the density of thermal, somewhat like the density of the thermal energy of a substance. So it's kind of somewhat like that. And you know what? For pneumatics and for general gas laws, we can look at temperature that way. Temperature is the density of the thermal energy in a piece of mass. So we'll just roll with that. Now, my father, who is a chemical engineer, when he kind of unpacked what temperature was for me when I was younger, and I kind of said, okay, so it's kind of like the density of the heat. And he's kind of like, well, as long as you say somewhat, it's okay to say that. So it's pretty close. We won't get into the density, we won't get into the thermodynamics and all the rest of it, but for moving forward with pneumatics and gas laws, that's exactly what's going on. So let's actually talk about what temperature is and unpack that a little bit more. So the difference between temperature and heat. I think you guys are probably okay with this, and I think you can imagine this. Let's say we had a 10-gram mass of thermal energy. Okay, so we had 1,000 joules in a 5-gram mass, and we also had 1,000 joules in a mass that was twice as much. So we have the same amount of thermal energy, and we'll discuss what thermal energy is in a minute, but just roll with me. So we've got this thermal energy in two masses, one is larger than the other. Well, the smaller one actually has a higher temperature. So the smaller one, same amount of thermal energy, half the mass, it's going to have twice the energy, or twice the temperature. Again, temperature is very much like the density. Okay, cool. So here's an example, more of a practical example. I'm not sure if you've used a grinder or not, but if you ever have used a grinder and the sparks are hitting your skin, they don't actually hurt. Well, what's up with that? Because they're like 2,500 degrees Celsius. Shouldn't they burn you? I mean, 2,500 degrees Celsius generally burns things. Yeah. Well, Each one of those sparks is so small, and the energy that's in them is packed into this little tiny little ball of energy, but I mean of mass, but it's not a lot of energy that's actually in there. But because it's so small, it actually ends up that the temperature is really high. So when those bits are flying and hitting your hand, unless they're actually hitting a spot on your skin that's consistent, it won't actually burn your skin, because the thing that burns your skin is the heat energy that's actually doing damage to your skin. So there's not a lot of heat energy in those sparks. Even though their temperature is 2,500 degrees Celsius, it's still not going to burn you. So I think that maybe helps unpack that a little bit more. Let's just continue with an example here. Okay, a little bit about what heat energy really is. So heat energy is added to a gas. Okay, the molecules of that gas start to move faster. Okay, so they have more kinetic energy to them, more molecular energy in their motion. Okay, so essentially heat energy is a transfer of gas converted to molecular kinetic energy. So the measure of the temperature of a gas is related to the molecular kinetic energy and the density of the molecules. Remember that the heat and the temperature are different concepts. So the concept of heat is really how fast the molecules are moving. And then the temperature is kind of how closely those molecules are together. And we can say that really the transfer of that heat energy out of that into the environment, that thermodynamic, is actually the temperature itself. Yeah, we can't actually feel that temperature unless it's coming out. And the way it comes out is those molecules are hitting the side of the container, and they're transferring their molecular kinetic energy into the side of the container, and then that actually goes out further and further. And we know that heat dissipates in 3 different ways. One is through convection, and the other is through radiation, and the other is through induction, which is when we're touching it. We'll talk about that a little bit more when we get into the last bit where we're talking about the full gas laws and maybe compressors and stuff. So we know that this energy is happening because of these molecules are moving around, and let's just say we increased the volume. Okay, so all the molecules still have the same molecular kinetic energy, but we're increasing the volume. Now those molecules are further apart from each other. Less of them are hitting the walls, and less energy is actually being transferred out per kind of area on the wall, if you can imagine that. So imagine a vessel that's this big, square, and it has a certain amount of kinetic energy of these molecules, and they're hitting the wall, and you put your finger on an area, or you study like a square centimeter of that area, you can see how, like, let's say you could see the molecules hitting that area. There'd be a lot of molecules hitting that area, and if you had your finger there, that molecular energy is being transferred into your finger, and you feel that as heat. Now, all of a sudden make it larger. Each little square centimeter of that area, of the outside of that, is now less interactions with these molecules hitting this side. So you're actually going to feel less heat transfer, which would be a smaller temperature. So I think we're good with what temperature is and how that all works, and it has to do with the density of all of this kinetic molecular energy. I think we can kind of move forward a little bit and discuss just temperature and how we actually look at temperature. And there are a couple different ways to take a look at temperature. So let's just define how we're going to look at temperature. We're going to say, okay, so temperature is capital T. And we know that, like, when we go for cross disciplines in science and technology, we have to say, okay, we know that capital T is used for Teslas, which is a unit, and also for a symbol, which is for period, and that's in, that's in electronics and electromagnetics and stuff. That's okay. Now we're jumping into the physics of pneumatics and just the physics of the gas laws, and we're going to use T for temperature. Okay, so we're good with that. So I think you're all right with it. It's a capital T for temperature, and we can measure them in Celsius or Fahrenheit or really cool things like Rakens and Reamers, but we're going to really focus on Kelvin. And one thing I wanted to mention is that we have degrees Celsius, we have degrees Fahrenheit, and we have, for kelvins, we just have kelvins. They're not degrees Kelvin or this many degrees. It's not a degree, it's Kelvin. So just kind of watch your words with that, so we're not discussing degrees Kelvin. We can discuss degrees Celsius and Fahrenheit. So what we're going to do is we're going to stick with Kelvin, and we're going to say we have to study everything with Kelvin, and the reason is because of absolute zero. What is absolute zero? Well, let's take a look at the Kelvin scale itself and kind of unpack that a bit. So what we have is the Kelvin scale is actually based on the Celsius scale. And the Celsius scale was defined from 0 to 100 with water. So if we had water at standard pressure, standard atmospheric pressure, 14.7 psi, and we put it to 0 degrees Fahrenheit, or more specifically, let's just freeze it. Let's remove heat from the water until it freezes. Now, that's a pretty standard kind of thing at 14.7 psi. So when it actually freezes, we'll call that 0 degrees Celsius. Now, let's boil it, again, at the same pressure, 14.7 psi A. And when it actually boils and starts to boil, we'll call that 100. Now, we'll break that up into 100 little pieces, and we'll call each one of those kind of 1 degree. Well, we can also call each one of those a Kelvin, actually. Now, Kelvin is based on Celsius, like I said. So each unit of Kelvin is equal to 1 unit of Celsius. So 1 degree of Kelvin, or 1 change in Kelvin, is the same in 1 change in degree of Celsius. So we base the Kelvin scale on Celsius, except the 0 for Celsius is based on water and the freezing point of water. The 0 for Kelvin is based on absolute 0. So let me just kind of go there. A block of ice, is there heat energy in it? Well, yeah, there's a lot of heat energy in it, actually. Although just the nature of ice is that it freezes at 0 degrees Celsius, but there's still heat in it. Remember, temperature is just the density of heat, and if we're actually going to put a number there, well, there must be some density of heat. So if we look at the Kelvin scale, and we say, okay, what if there was 0 degrees Kelvin? What would happen? Well, that would mean there's no heat. So when we go down to 0 degrees Kelvin, we're looking at absolute 0, where there's no heat in anything. So we're actually looking at temperature from how much heat energy is in it. And if we start with 0 heat energy, then we're at 0 Kelvin. So what we're going to do from now on is we're going to do all of our calculations in the gas law relative to the temperature scale of Kelvin and not Celsius, because we need that 0, because really we're studying how much heat is in it. We're not really studying the density of the heat. We're just studying, hey, how much heat is in this thing? And we look at that in temperature. So let's just continue on here and kind of take a look at this. So imagine this. So we have some gas, and the temperature is 20 degrees Celsius. Okay. And so heat is added to it until it increases to 40 degrees Celsius. So we went from 20 degrees Celsius to 40 degrees Celsius. Did we double the amount of heat in there? We added heat into the system until it went from 20 to 40. But did we double the amount of heat? Well, we doubled the number of the temperature. But remember, that temperature scale is relative to 0, which is actually still 0 degrees Celsius, still has a lot of heat in it. So the question here is, did we double the temperature? Well, the answer is no, not quite a bit. We did not double the temperature. We added more heat and the temperature went up a bit, but when we're actually doubling temperature, we're doubling the amount of heat in it, and that's relative to 0 or to no heat at all. So why is the temperature of an object, a gas, is directly related to the amount of heat energy that exists in that object. So if we say we're going to double the temperature, well, we're doubling the amount of heat. Well, then we have to say, well, how much heat was in it in the first place? That's relative to absolute 0, where there's no heat energy. Okay, so there's a cool example where we just take a look at the Kelvin scale again, and the same example where we can say, you know, that 20 degrees is actually just it's a tiny little space on that huge scale of Kelvin that starts way, way, way below. And actually Kelvin, as you can see, way below is 273.15 degrees, way below 0, or that's at 0. So it's 0 degrees, sorry, I said degrees again. 0 Kelvin is actually 273.15 degrees below 0 degrees Celsius. It's really small. So you can see that little tiny 20. So let's take a look at doubling pressure, just so you can wrap your head around, because I think you guys understand this a little bit, just so you can wrap your head around what it's like when we double temperature. So a gas has a pressure of 20 psi G, gauge pressure, okay? What happens if the pressure doubles? Okay, does it go to 40 psi G? Well, no, it doesn't. because we know when we're doubling the pressure of something, we actually have to turn it to absolute pressure and then double that and then convert it back. So you have 20 psig and you double that, you actually get 54.7 psig. Because we have to, when we're doubling the pressure, well, we have to do that relative to absolute pressure. Okay, so in that same way we do the temperature like that. So let's just take a look at an example of temperature. So when we have temperature conversions here, so a gas has a temperature of 33 degrees Celsius. What is that in Kelvin? Okay, so it's 306. All we're doing is adding 273.15. That's it. So you just add that number, and then you're good. So you double that, sorry, and we know that that's the answer. So what if we double that? What if we double 33? Well, if we double 33, okay, what we're going to do is we're going to add heat to that gas, and we're going to double it, and then what we have to do is convert it to Kelvin, and then we're going to double that temperature, and then the answer is this. So we convert it back. So take a look at this. So if you take 33 degrees Celsius and double that temperature, it's actually 306.15 degrees Celsius. So that's the kind of the relative concept there. So I think we've unpacked temperature a little bit enough to kind of move forward. So let's actually move forward and talk about the 3 gas laws, and then we'll jump into the general gas law. So there are 3 gas laws. One is Boyle's, and the other is Gay-Lussac's and Charles, and they all studied, all 3 of those guys studied 2 of those 3 things. So there's pressure, temperature, and volume. And they took 2 of those, and I think this is important just to kind of pause here and remember this. They made one of them stay consistent, and they changed the other. So, and each of them chose the other 2. So I think this will make sense. Let's just go and continue here. So what Boyle did was he looked at pressure and volume. And I think I'm talking about this one first because it's easier to wrap your head around it. So the question is here, what happens to the pressure of a gas inside the container if we increase the volume of the container, but we keep the temperature the same? Okay, so we have a volume, we have a certain volume in a container, and we're increasing the volume. What happens to the pressure? Well, I think you kind of can put your head around this. Let's take a look at it here. So we've got 70 molecules on one side, 70 molecules on the other side. It's kind of a before and after kind of thing. Okay, so what we're going to do is we're going to have the same temperature on either side, and right now we're doubling the volume. Okay, we double the volume. Now remember, we have the same amount of molecules. We get the same number of molecules. So from there, what's going on? Well, what's the new pressure? Well, it's half. We've just gone down by half. So, and you notice that it's psi. We're looking at pressure relative to absolute pressure. So let's take a look at this the other way around, where we're decreasing the volume. Okay, so we've got a certain amount of pressure in a system or a volume, and then we're going to decrease that volume. What happens to the pressure? Well, I think you guys can figure this out. I think it's good as long as the temperature is the same, and we're going to have the same temperature, and now we're increasing the volume, decreasing the volume by half. What's going to happen to the pressure? Same number of molecules. Nothing's happened. We haven't added anything. It's important to just kind of highlight that. Okay, so what's the new temperature? Well, 40 psi relative to absolute. Well, we're just going to double it. I think you guys get that. Okay, so let's move forward and take a look at Gay-Lussac's law. Okay, Gay-Lussac, what he did was he studied pressure and temperature. So he left the volume the same. And I did a really cool video on Gay-Lussac, so you guys make sure you watch that. I actually did a video in my lab of all 3 of these in action. Actually, the final one, Charles' law, I did a video, but I didn't actually do anything. I just discussed it, but it's nice and quick. So watch those, because you can see all of these laws in action. And it was simple to do it in my lab. Okay, so let's continue here. What happens to the pressure of a gas inside a container if we can increase the temperature? Okay, so the volume is the same. Okay, and what happens? Well, you can watch that video, but let's continue. Okay, so we've got kind of before and after. So, yeah, what are the molecules? So why are the molecules in motion anyway? Well, it's because they've got heat, they have temperature, okay? So they've got heat energy in them. So the higher the temperature, the faster the molecules, and the more momentum they have as a result, they can apply a greater force to the wall. Okay, so let me actually stop for a minute and talk to you about Blaise. Okay, Blaise Pascal, really very cool guy, scientist from the 1700s, very super awesome guy. And he's the father of gas laws, or he's the father, I want to say the father of pneumatics, because pneumatics is is a study of captured air doing things to actually make forces for us and a lot of control things and stuff. So pneumatics is a science or a technology that was based off the science that Pascal did, Blaise Pascal. So I actually read this when I was studying physics. So I was young, about your age, and I thought it was fascinating. And I read this book. So this is a book called Pensées, which is French for thoughts. And Pascal, what he did was, he was fascinated with air. He studied air pressure. He did a lot of really cool things. It's more of a metaphysical book because he talks about philosophy and stuff like that as well. But the philosophy of science was pretty wild. It was a great book and a good perspective of a brilliant person's mind. So thanks, Pascal, for being the father of, air, of the study of air. So what he did was he found, this is interesting, I'm talking about this for a reason. So he found that what's going on is that pressure itself, the force that's actually happening on a vessel to kind of push it out, has to do with the molecules hitting the vessel at a right angle. So they're actually applying force that's going out. So the more molecules hitting the outside of the vessel itself at a right angle, we kind of average all of the molecules hitting, and if we average them all hitting at a right angle, that's the amount of force that's being applied on the outside. But that's kind of how we look at what pressure is. Because remember, we look at the force of those molecules hitting the wall in a particular area. We can't study the whole area. I guess we could if we took what's the full area of this vessel, and then we could see what's the total force. But really what we're looking at is kind of a ratio or rate. And that's what pressure is. So he came up with that concept. Pretty brilliant man. So let's continue with this. And what we're looking at is we're looking at pressure and temperature. We're going to change the temperature and see what happens. Okay, so same amount of volume. We are not changing the volume, but we're doubling the temperature. Okay, and we're looking at that in Kelvin. So what goes on with the pressure? Well, we get the same number of molecules, and we're looking at the pressure. Well, if we double the amount of heat energy, or double the temperature in Kelvin, we're going to double the pressure. We have 80 psi. Cool. So let's continue and look at this from another example. We're going to cool it down. So what happens to the pressure inside a gas if we decrease the temperature of the gas, but we also maintain the same volume? Well, going back to Blaise, right, we're going to have less of those molecules. They have less molecular energy to them. And they're hitting the vessel. Actually, they're hitting the vessel, the outside of the wall of the vessel, actually less because they're slower. So, and their kinetic energy hitting the outside of the wall is less as well. So the pressure is going to go down because pressure is really the amount of force that's applied per area. Okay, so let's continue here and take a look at this. So they're slowing down and they're hitting the walls less. Now, we've got this situation where we've got the same volume, absolutely. Now we're going to half the temperature. We're going to half it. What's the pressure? Well, the pressure is actually going to go down as well. So pressure and temperature are also directly relational. They're linear and they're directly relational. Okay, so one goes up, the other goes up, one goes down, the other goes down. Okay, let's take a look at Charles' law. So Charles' law was a pretty cool dude, and what he did was it was kind of difficult for him to study this stuff because he took volume and temperature and he had to keep pressure the same. So it was kind of difficult for him to study this stuff. And I think the best example I can really talk about is, and I talked about it in that video that you can watch, but I mean, think about this. If you take a balloon, has a certain amount of pressure in it, and you put it in the freezer, what happens to it? Okay, so what happens to the volume when you change the temperature? Now, the pressure in that case also changes to some degree, but I think it makes sense to you that if the actual temperature changed, the volume would change, in that when the temperature decreases, the volume will also decrease. So what happens to the volume of a container if we increase the temperature of the gas? Well, for it to maintain the same pressure, for the same pressure to stay that way, it's actually going to have to change. It's going to have to increase. Okay, so let's take a look at this. We've got the same pressure, and we're doubling the temperature. Okay, so what's going to happen? Remember, we've got the same number of molecules that are in there. And what's actually happening is for those molecules, they're moving faster. They have a lot more kinetic energy because we've added heat to them. Okay, so for me to maintain the same pressure, for them to actually be applying, going back to Blaze, thank you very much, for them to actually be applying the same amount of force. Let's say we have this square area right here. So I've got these molecules captured in this vessel, and I heat them up. I put more energy into them. Now they have more kinetic energy. So there are actually more molecules hitting the same area in the same amount of time. So there's actually a greater force because they have greater energy. So for me to keep that pressure the same, I've got to increase the size of the area. So that's what's going on. For me to maintain the same pressure, I have to actually increase the area. So that's kind of what Charles was doing. So let's move on and actually talk about the general gas laws. What we're going to do is we're going to actually put it all together, put all of these formulas together. I kind of like this slide because it has the ratios. It kind of looks at how they interact with each other, and it shows that Boyle's law is inversely proportional. So we can say that pressure and volume are inversely proportional. I think that just makes sense if you wrap your head around that. If I increase the pressure, if I decrease the volume, the pressure is going to increase. So, and as far as Gay-Lussac's law goes, we can see that pressure and temperature are directly proportional, and all of these are linear as well, which I mentioned several times. And then volume and temperature are also directly proportional. One goes up, the other goes up, stuff like that. So, and then these are the formulas, and more specifically, we have to focus on the fact that we have like kind of a T1 and a T2, and a V1 and a V2, and a P1 and a P2. So the 1 is the before, and the 2 is the after. Okay, let's move on and look at some examples here. So if we put them all together into the general gas law, then we end up with this formula. So we can put all three of those together and talk about the general gas law, where all three of them are changing. So very much like that balloon example. So if I were to take that balloon and throw it in the freezer, the pressure is actually going to change, the temperature is going to change, and the volume is going to change. And they're all going to change. So we could study that with the general gas law. The pressure doesn't change as much as the other two, but it still changes. Now, what I need to do is just reiterate kind of some understanding about what we're talking about, and then I'm going to show you an example of the general gas law. Okay, good. So, there is some relationship between volume, temperature, and pressure. We know that. The relationships will establish an interaction together. So the relationship established, the actual mathematical relationships establish how they interact together. So if one of these variables change, we can predict how the other changes. But, and there's the but, we make sure that there are two things going on. We have to make sure that the volume, the pressure, and the temperature are describing the same gas. So we can't talk about gases either outside a vessel and inside a vessel, both of them, or maybe the gases in two vessels. We're only talking about we're talking about the same gas. And we also make sure that it's in a closed container. We can't do this actually you can do it with the atmosphere, but looking at the atmosphere as one full closed container. Okay, good. So now let's move on and take a look at an example of the gas law, and then we'll be done. So the general gas law, and then we'll be done. And we're going to kind of talk about compressors to some degree. So the basic unit is Kelvin. We know that. We're good with that. And Boyle's law example, here's a question of a Boyle's law example. A question has an internal volume of a certain amount of cubic feet. Now, we're talking about cubic feet. This could be cubic inches, cubic millimeters, doesn't matter. As long as we're consistent, it'll work out. And a pressure of 100 psi-G. If the volume is increased, so we're increasing the volume, and what's the new pressure? Well, Boyle's law states that temperature remains the same, okay? So the temperature is constant, okay? So what's going to happen? Well, let's take a look. We'll have to convert it because our pressure is in gauge pressure. I have to convert it to absolute. Okay, that's easy. So I'm at 114.7 psi-A. Okay, let's continue. I'm just going to throw it into the Boyle's law, and we'll isolate for the unknown. P2 is the unknown. We'll put our numbers in, and we're looking at 65.4 psi-A. Now, if we wanted to convert that back to G, psi-G, that's not a problem. So just kind of going back again, we've got 0.56 and we're increasing it to 0.98. So we're increasing the volume. We start out with 100 psi-G, or more specifically, we're starting with 114 psi-A, and our end result is 65. That makes sense because we increased the volume. Okay, so let's continue on here. Gay-Lussac's. Okay, so a gas has an initial temperature of 24 degrees Celsius, so we're going to have to convert that to Kelvin. Okay, and we've got 29.4 psi-A. Sweet. Okay, so if the temperature increases, right, because Gay-Lussac's is all about temperature and pressure. So for increasing the temperature to this degrees Celsius, what is the new pressure? Okay, and we have to keep the volume the same. All right, we'll just throw the numbers into the formulas, although we have to do some conversion. We have to convert that Celsius into Kelvin. So we've got the two Kelvin numbers. We've got the before, the T1 and the T2, and we've put those into Kelvin, or more specifically, we've got the C numbers and we put them into Kelvin. So we've got those two. Now, we just throw them into the actual gas law, or Gay-Lussac's law, and we end up with 57 psi. Okay, well, that's cool. Let's just go back and take a look at it. So we started with 297 Kelvin, and we're going up to 549 Kelvin. Okay, so the pressure is definitely going to increase. Our initial pressure was 29.4. Our final pressure is 57. I think that makes sense. And we can see that it's a linear relationship. Okay, so let's continue on here. So a question, okay, this is the general gas law. We're putting it all together. I didn't do a Charles law. So we're putting it all together. And we're saying, okay, so a gas has an initial temperature of 21 degrees Celsius, a pressure of 29.4 psi, and a volume of 75.6 cubic inches. If that volume was cubic meters, was cubic millimeters, was cubic inches, was cubic whatever you wanted to make up a new unit for yourself, it would not matter. As long as it's consistent, it's good. So we don't have to convert the volume like we do temperature and pressure, because volume is relative to no volume. So I think you're good with that. Okay, so during the compression, oh, there's a compression. Okay, during a compression process, the volume decreases to 12.1 cubic inches. Okay, so we've got a certain amount of volume and we're decreasing it. And what's happening is that as we decrease it, those molecules are getting shoved in closer together. Now, we're not adding heat. We're not adding molecular energy, molecular kinetic energy. We're not doing that. They already have the same molecular kinetic energy. So let's just think about Blaze here. Now, that vessel is smaller. There's the same amount of energy in there. So the molecules that are hitting the wall in there, well, they're hitting the wall more often now. And that force is the amount of impacts of those molecules are greater in any particular area. So obviously the pressure is going to go up. But you know what? Wait a second. Temperature is the density of that energy. So we have the same amount of energy in a smaller volume, so its density gone up. So it went up. So the temperature goes up. Okay, so the pressure goes up, the temperature goes up, and the volume decreased. Now remember, the general gas law is where they all are changing. Now, what we do in the compression cycle is we vent that heat. And heat likes to vent. It loves it. It's like, I'm out of here, dude. I don't want to be here. Heat really dissipates really well. So heat can leave through radiation. Heat can leave through conduction. So induction and convection, pardon me. So heat can leave through induction where something's physically touching it. Now in compressors, this is a compressor example. In compressors, we don't actually have physically things touching it, although we can have, I guess, a liquid-cooled compressor, but I'm not even sure if they exist, but we could make one if we really needed to. So I imagine they probably do exist when you have to do really, really high pressures. I don't know about those, but let's continue. So we've got to let that heat leave, and heat can leave in three ways. One is it radiates, and the other is convection. So that's really how a lot of the heat leaves a compressor, because a compressor has fins on it, and air is going over it, and we could put a fan over it. Actually, a lot of compressors do have fans over them to remove that heat. But why do we want to remove the heat? I mean, you know, what's wrong with some hot gas? We can still put hot gas into pneumatic actuators. It's not a problem. They still work. As long as it's not super hot, it's not going to damage them. So what's the issue? Well, the issue is that heat dissipates. So that gas will lose its temperature. And if the gas loses its temperature, it will affect its pressure, because temperature and pressure are linked. So if we take the gas out of our compressor and we don't let the heat leave, that heat ends up in the tank. Now we've got a pressurized gas in a tank, and it's hot. Well, if I just let it sit there, it's going to cool down. Well, the pressure will decrease. So what I want to do is, I want to actually take the air coming into the compressor, compress it, take all of the heat out of it, and then put it into my vessel at the same temperature. Because it's going to end up being the same temperature as it came into the compressor within a certain amount of time, because all that heat will dissipate. So the process of compressing, really, we want to take a lot of that heat out. So this example discusses that. Although, when I say a lot of the heat, we don't take all of the heat out. We could, but it's really costly. So we just do as much as we can to take the heat out. Let's take a look at this. Okay, so now we know it started at 21 degrees Celsius, and we know the volume decreased. And the temperature went up a little bit. It just went up to 30 degrees Celsius because we vented a lot of that heat. But we know those three things are all interacting together. So actually, what do? Well, in this case, we have to convert those temperatures to Kelvin. We have a before and an after. Okay, that's done. We have 294 and 303, pretty close, but there's a change. So that's going to affect our pressure to some degree. Now, we'll take a look at this. Take our general gas law, and we're going to solve for the unknown, right? So on the left-hand side, we're solving for P2 because that's what we're after. We want to know what the final pressure is. Now, if we take a look at this, I'm just going to go back and take a look at this. So we're starting with 29.4 psi, and we're decreasing the volume actually by 6 times. So 75.6 12.1 goes into 75.6 6 times. So we're decreasing the volume by 6 times. So you'd think the pressure would go up by 6 times. Well, okay, so 176, pardon me, psi A is 6 times 29.4. So if I took 29.4 psi and I increased that pressure by 6 times, I'd end up with 176 psi A. But look at the pressure. It's a little bit more than that. It's 189, and the reason is because we've left heat energy inside. We've left heat energy in there, and some of that extra heat energy is making the molecules hit the surface with a little bit more energy packed in. The density of that energy is greater in any particular area. So that increases the pressure. So that's what's going on. So that's the whole thing. So we're done. So you guys are now experts at this stuff, and what you're going to do is, for your homework, you're going to be actually taking a look at these examples of all of these gases going up and down. You're going to be taking a look at the 3 gas laws and the general gas law, and I want you to do some temperature conversions. I need you to kind of practice doing the temperature conversions, and then I think we're good. Okay, bye.